Hello, this is Dr. Imran Khan, and I will give you a lecture on Introduction to Digital Integrated Circuits. You can also see my email IDs on the slide. So if you feel any problem, you are welcome to contact me via email. Okay, let's start our lecture, Introduction to the Digital Integrated Circuits. Outline of our lecture is we will start from introduction, then we will discuss history of digital integrated circuits. We will also discuss Moore's law and integrated circuits evolution, and in the end we will discuss some challenges in the IC design. Introduction. Before starting our lecture, I have two questions to you. Why is designing digital ICs different today than it was before? And second question is, will it change in future? Answer of the first question is because you want to integrate more and more number of transistors inside the small silicon areas, because you want your chip more powerful compared to the previous chip. So that's why you want to have more and more number of transistors inside the small silicon area. So you are scaling down the transistor. Scaling down the transistor means that you need the different design techniques, and also you will like to have the low power designs because you will like to control power dissipation inside your digital ICs. So these are the main reasons your integrated circuit design techniques are changing. So the answer of the second question was, will it change in future? Answer is yes, because in the future you will have even more powerful ICs, and you will like to have more and more number of transistors because you will like to have more functionalities in your integrated circuits. So that's why the answer is yes. Okay, let's start from the history. As you know that BJT, bipolar junction transistor, was invented in 1947, and the single transistor integrated circuit was built on 1958. Similarly, invention of first CMOS logic gate was in 1963, and Intel introduced its first microprocessor, Intel 4004, in 1970s. So in 1978, your first VLSI based system was introduced. VLSI means very large scale integration. So what is VLSI circuit? You know that VLSI stands for very large scale integration. A circuit that has 10K to 1 billion transistors on single chip is included in VLSI design. Still a growing number of transistors on chip, and we will discuss about the integrated circuit, basically technique where many circuit components and wiring that connect them are manufactured simultaneously on a compact chip or die is called integrated circuit. So here you will see something on the transistor revolution. So first transistor, your BJT, was invented in 1947 by Bardeen in Bell Labs, and first bipolar junction transistor was built by Shockley in 1949. First bipolar digital logic gate was introduced by Harris in 1956. First monolithic IC was introduced in 1959, and similarly first commercial IC logic gate was introduced in 1960s. So here is some transistor revolution. So here in the slide you can see the first electronic computer in 1946. So here you can see that this computer is very big, So this computer was based on the vacuum tip technology, and even the laptop you are carrying today or the mobile phone you are carrying today is millions times powerful than this computer. This happened because of the revolution in transistor technology. Now your transistors are in nanometer technology, so that's why you can introduce billions of transistors inside small silicon area. So this was the only thing you were able to design the powerful computers. So the transistor revolution, this was the first transistor by Bell Labs in 1948. In the slide, you can see first integrated circuit by Texas Instruments in 1958. Intel introduced its first microprocessor, Intel 4004 microprocessor in 1971. This microprocessor was having 1000 transistor and clock frequency was 1 megahertz. Similarly, Intel introduced some other microprocessors. So here you can see one example, Intel Pentium 4 microprocessor. So the Pentium 4 microprocessor was introduced by Intel in the year 2000. It was having 1.5 gigahertz clock, and it was fabricated on 180 nanometer process technology, and it was having 42 million transistors. In year 2002, Intel introduced another Pentium computer. So it was having 2 gigahertz clock frequency, and it was based on 130 nanometer process technology, and it was having 55 million transistors. In year 2005, Intel introduced another microprocessor. It was 3.8 gigahertz based on 90 nanometer technology, and it was having 120 million transistors. So here you can see the trend in microprocessor design. So you have more and more powerful microprocessors. The other chips. So here you can see examples of other chips, IDT, IBM, HP. So these all chips are based on the advanced process technologies, and these are the examples of revolution in your transistor technology. In this slide, we will discuss Moore's law. In year 1965, Gordon Moore noted that the number of transistors on a chip doubled every 18 to 24 months. He made a prediction that semiconductor technology will double its effectiveness every 18 months. Gordon Moore was founder of Intel, and his prediction drove the semiconductor industry almost for 60 years. Transistor cons. So here you can see the trend between the number of transistors and the number of years. In year 1975 to year 2020, so you can see a big change in number of transistors. So in year 1975, you can see only few tens of transistors in your digital ICs, but nowadays you have even 15 billion transistors inside your microprocessor. So this happened because of the revolution in transistors. You are continually scaling down your transistors. So here you can see that the Moore's law in microprocessor. Here you can see the trend. The number of transistors are increasing with the number of years. It means that the functionality of your integrated circuit is continually increasing with the number of years, because you are integrating more and more transistors inside the small silicon area. So here is almost 2 times growth in 1.96 years. Frequency. In the integrated circuits, frequency also doubles every 2 years. So here you can see the trend between the frequency and the number of years. Power dissipation. As the number of transistors are increasing in the small silicon area, each transistor dissipates some power. And you know that nowadays you have the chips with billions of transistors. So that's why power dissipation is a major problem in the integrated circuit design technology. Here you can see the trend between the power dissipation and the number of years. Power dissipation continually increasing with the number of years, because you are integrating more and more transistors in the small silicon area. Here you can see the trend. Yeah, so it's continually increasing power dissipation. So the power dissipation is going to be a major problem in integrated circuit design. So here you can see the trend of power dissipation between year 1971 to 2008. So here you can see that the power dissipation is continually increasing, because nowadays we have more complicated chips with billions of transistors inside small silicon area, and they are dissipating a lot of power. Power density. Here you can see the trend between the power density and the number of years. So power dissipation is continually increasing. So here you can see that the power dissipation in Pentium 6 computer is almost equal to the power dissipation in hot plate. So here you can see the power dissipation in nuclear reactor and rocket nozzle. So you need to basically control power dissipation inside your integrated circuit. Power dissipation decreases the reliability and it causes many problems like electromigration. So here you can see the trend between the power dissipation and the number of years. Power dissipation is increasing because the number of transistors are increasing. Now you have integrated circuits with billions of transistors inside small silicon area. Here you can see a 3D graph. It is showing the relationship between number of years and the microprocessor introduced by the Intel, power dissipation, and the number of transistors. So this is a 3D graph, and you can see the trend between the power dissipation. Here you can see with the number of years, the number of transistors are increasing inside the integrated circuit. With the increase in number of transistor, power dissipation is also increasing. So here you can see the trends in semiconductor industry. So one example is iPhone 11. This device is having 8.5 billion transistors inside the A3 processor, and this processor was built on 7 nanometer process technology. You can see the difference between the devices in 1990s and 2020. So there is a huge difference between the device performance. This happened because of the revolution in transistor technology. The number of transistors are continually increasing inside the digital circuits. So this is the only reason that the performance of ICs is increasing. So here are some challenges in the digital design. This DSM stands for Deep Submicron Technologies. So here we have some microscopic problems and some macroscopic problems. Microscopic problems include ultra high speed design, your interconnects, crosstalks, noise, and the power dissipation, clock distribution, reliability, while the macroscopic issues include time to market, and you know that you have the millions of gates, high level abstractions, etc. Here you can see the technology direction between the year 1999 to 2014. So here you can see the difference in feature size, logic transistors, cost per transistor, clock, chip size, wiring level, power dissipation, power supply, and many other things. So the feature size in year 1999, it was basically 180 nanometer process technology. In year 2002, it was 130 nanometer process technology, while in year 2014, it was 35 nanometer process technology. Similarly, the number of transistors are increasing. In year 1999, the chip was having transistor around 6.2 millions, while in the year 2014, the transistors was around 390 million. So you can see the number of transistors are continually increasing, cost per transistor is decreasing, clock frequencies are increasing, and the power supply is also decreasing because you are interested in low power designs. So these are the technology directions. Why scaling? As we discussed before, we are scaling down our transistors. We are scaling down our transistors because we want to have more and more number of transistors inside a small chip, because we want to get more and more functionality. Technology shrinks by 0.7 per generation. With every generation can integrate 2 times more function per chip. Cost of function decreases by 2 times, but there are also some issues. How to design chip with more and more functions? Design engineering population doesn't double every 2 years. Hence, a need for more efficient design methods are required. So here are some design abstraction level. So if you look on your integrated circuit, you can see the system level design. Inside your system level design, you have many modules, and inside every modules you have the logic gates. Inside the logic gates you have logic circuits, and inside the logic circuits you have the device level fabrication. So this is the design abstraction level in the integrated circuit design. Design matrices. We can evaluate the performance of our digital circuit by cost, reliability, scalability, speed, power dissipation, energy to perform a function. So these are the key parameters in designing an integrated circuit. Cost of an integrated circuit. There are two types of costs in integrated circuit design. First is NRE. It is non-recurrent engineering cost. Second one is recurrent cost. Your NRE cost is only one-time cost. It includes design time and effort, mask generation, etc. Recurrent costs include silicon processing, packaging, test, volume, chip area, etc. Here you can see the trend. NRE cost is increasing. Your 70 nanometer ASIC will have $4 million NRE. Cost per transistor is decreasing. So here you can see a relationship between cost per transistor and the number of years. So here you can see cost per transistor is continually decreasing. So here are some pictures of the clean room. Here you can fabricate your integrated circuit. So this is not the topic of our lecture today, but I was just interested to show you some pictures of the clean room where at least you can fabricate your integrated circuits. So we will discuss fabrication of integrated circuit in another lecture. Okay, thank you very much.